For more videos like this for Discrete 1, you can take a look at Sarai Studies. Link is in the description box below. We're told to show or prove that if n is a positive integer like 1, like 2, like 3, and so on, then this is true. Now this is what we call our claim or our P of n. So this is a proposition because it could either be true or false, but it's a proposition that depends on what the n value is. So if you go back, n should be a positive integer. So this tells you that you're dealing with the set of all integers that are positive only. So you don't include 0, you don't include negative numbers, so you just start with the positive ones. So 1, 2, 3, and so on, which also happens to be the set of all natural numbers. So you'll notice that when you're doing proofs by induction, you're going to be mostly dealing with these domains. They're the same, by the way. But the idea is that n can be equal to 1, or n can be equal to 2, or n can be equal to 3, or n can be equal to whatever nth positive integer, because there's infinite amount of them. And so you can plug 1 to P of n. In other words, to this claim, you can plug 1 wherever you see n and see if it's true. You can plug in 2, you can plug in 3, but we don't have the time to plug in infinite amount of positive integers. So we have another method called proof by induction, and there's 3 steps. The first one is the basis step, second is the inductive hypotheses, and the third is the inductive step. Now to never forget these steps, I'm going to show you the domino analogy. So just like we have n positive integers, so infinite amount of positive integers, just imagine infinite amount of dominoes. So for each step, I'll give you a visual as to what's happening with the dominoes. But before anything, we can actually rewrite our claim so it's more compact and simplified. So when you see these little summations, you can just use sigma notation. So we can rewrite this to say we're adding from one point to another. So our initial point, I, is just going to be the last thing that you're adding and the first thing. You're going to take these two things, set them equal to each other, and solve for the variable. In this case, the variable is already solved for, which is really great. So whatever number you get, that's going to go here. So that's 1. And then you're stopping at the last value in your domain. So our domain is a set of all positive integers. We have an infinite amount of them. We can call the last one n. So that's going to be n. And then what's going to go here is really the last thing that you're adding. So it's n, but wherever you see this variable, which is this whole thing right here, you're going to replace it with this one. So it's really going to be I. And this is more apparent. Let me give you an example. If you have another one like this, so this is this stuff, and this is this part. We can write this part with a sigma. I is equal to, you set these two equal to each other. So 4n minus 1 is equal to 3. You solve for the variable. So plus 1 plus 1. These cancel out. This becomes 4 divided by 4. These cancel out. We're left with 1. So n is equal to 1. The number you get here goes here. To get this, assume that the domain is the same for this problem. So it's all positive integers. You have infinite amount of them. You can call the last one n. So it's n. And then what goes here is the last thing that I'm adding. So it's going to be 4n minus 1. But wherever you see the variable that you see at the top, you're going to replace it with this variable at the bottom. So it's going to be 4i minus 1. So that's the sigma version of this. So similarly, the last thing I was adding was n, but the rule was wherever you see this variable here, you have to replace it with this one. So since it was the only variable, the only thing there, it was just going to end up being completely replaced with I. So this part, we wrote it with sigma notation, and then we can just drop down this part. So this is our claim simplified, and now we can get started with our proof. So we're going to say we're doing a proof by induction on n, and our first step is to show that the claim, so our claim here, is true for the first n. So that doesn't necessarily mean that it's going to be always 1. Sometimes it could be 2, sometimes it could be 3. They'll specify if they want it to be greater than 2, so then you don't include 1 and you start at 2. But at the end of the day, when doing summation problems, it's always going to be this number right here. That's what we call our base case. So in this case, that is 1. So in the domino example, all this means is that we're showing that the first domino falls. So fall in the analogy means that the domino that fell satisfies the claim. So in this case, n is equal to 1 is equivalent to our first domino. We're trying to show that n is equal to 1 falls for a claim, that our claim is true for n is equal to 1. So all that means is you're going to take your claim right over here, drag it down here, and wherever you see n, you're just going to replace it with 1. So this is going to be 1, 1, and 1. And your goal is to show that this side is equal to this side. That's what your claim is saying. So some people like to define this as the left-hand side and this as the right-hand side. So at the end of the day, the left-hand side of the equation, you start at 1, you're going up until 1, so your I is 1. So you're not really adding anything because you're stopping where you started, so your answer is just 1. And then on the right-hand side, 1 plus 1 is 2, times 1 is 2, divided by 2, that becomes 1. So your right-hand side is also 1. So because they're the same, because your left-hand side is equal to the right-hand side, then you showed that your claim is true for n is equal to 1. So you show that the first domino fell. So that is our first step. Our second step is where we assume that our claim, so this right here, is true for some n is equal to k. Now in the domino analogy, k is just a random domino. So let's say I pick this random domino, I'm going to label it k. In our problem, k is some positive positive integer. So I'm going to pick a random positive integer. I'm going to label it k. I don't know what it is. It's just going to be called k. So where k is random and it is fixed, meaning we're going to pick one fixed domino. It's not going to change. It's not going to be more than one. It's just going to be that one domino. In our problem, that means that we're going to pick one fixed positive integer. And it is in the same domain. In the analogy, that means I'm not going to pick a domino from another set of dominoes. I'm going to pick a domino from this set of dominoes. In our problem, that means I'm not going to pick a number such as 1/2. 1/2 is not even a number in the same domain. We're in the domain of positive integers. So whichever number I pick, whatever number that is, k, is going to be a positive integer. It's going to be a domino in the same set. So in the analogy, I'm going to pick a random domino, let's say this one. I'm going to call it my kth domino, and I'm going to assume that it falls, which means I'm assuming the claim is true for that domino. All that means here is you're going to take your claim, drag it down here, and wherever you see n, you're just going to replace it with k. So I'm going to put k here, and k here. And that's it. That's all we're doing. Just leave it like that. Move on to the third step. The third step is showing that the next domino, the k plus 1 domino right over here, actually falls. In other words, we show that the claim is true for n is equal to k plus 1. So just the next domino. In our problem, in the second step, we assume that for some positive integer k that we picked, the claim was true. But in this step, we're showing that the claim is true for the next integer, which is just the same integer plus one more. That's how we get the next one. So all you're doing is take your claim right over here, drag it down, and wherever you see n, which is here, here, and here, just replace it with k plus 1. Just like that. And now your goal is to always use the inductive hypotheses. Like if you don't use the inductive hypotheses, then that means you didn't do induction, or that means that you could have done another proof. So your inductive hypothesis says that this specifically is equal to this. And here you have something similar. The only problem is that here you have a plus 1, here you don't. But a cool thing you can do with sigmas is you can split them. So to give you a visual as to what this is saying I'm going to start at the first domino, so right here. And I'm going to add up, so I'm going to go all the way up until the last value, which is k plus 1. So the last domino, this one right here. So this little area represents the sum from the first domino up until the last domino. But remember that I want this. So if this distance here is this, then up until k is just going to be the first one up until k. So this part right there. So I can split this whole thing, into this. So I'm going to drag this down. And then I can add what's missing, which is just the last value. Because if this part is the sum from the first domino up until the kth domino, then what's missing is just the last domino, which is just k plus 1. So what's going to go here is k plus 1. And then we can drop down everything else right here. In other words, I can look at this and realize I want this, so I'm just going to take everything but that plus 1. So I'm going to add up until the second to last domino. So this area, that becomes this. And then I'll just take care of the last value that I was going to add up, which is this last one here, this k plus 1, which is this little part. So that's this, which is the last domino. And now I'm able to use my inductive hypothesis that says that this here is equal to this. So now that I see this, I can replace it with this. So I'm going to take this and have this be equal to that. And then you want to say you use your inductive hypotheses right here. And then you can drop down everything else. And now this is what's considered your left-hand side, and this is what's considered your right-hand side, and your goal is just to show that these are equal to each other at the end of the day. You're really just trying to simplify the left-hand side to give you the right-hand side. With these summation problems, everything after this is just algebra. So I'm just going to do the work here. Here we can distribute, so this would become k squared and then plus k all over 2. And we still have plus k plus 1. On the right hand side, we have plus 1, that becomes a plus 2. So this is equal to k plus 1 times k plus 2 all over 2. On the left hand side, this is over 1. And we can add these fractions. So I'm just going to delete this for a second. The common denominator is 2. Then you ask yourself, does this numerator have 2 in its denominator? Yes, so you leave it by itself. And then you do your plus sign. And then does this numerator have this in its denominator? No, it has only 1. I don't see 2. So you're going to take this numerator, k plus 1, and you're going to multiply it by what's missing, which is 2. And so we end up with this. Then here you can distribute the k plus 1. So k times k, that's k squared. K times 2, that's plus 2k. 1 times k, that's k. 1 times 2 is 2. And then all over 2. On the left hand side we have k squared plus k, and then here that becomes 2k plus 2 all over 2, and on the right hand side we have k squared plus 3k plus 2 all over 2. Here this is 1k plus 2, that's 3k, and then the k squared and the plus 2 can just drop down, and we have it all over 2, and then we can drop this down right there, and look at what we have. We have k squared plus 3k plus 2 over 2 is equal to k squared plus 3k plus 2 over 2. So we showed that the left hand side is equal to the right hand side. In other words, we showed that our claim is true for n is equal to k plus 1. So now we say, therefore, by induction, and we just drop whatever they wanted us to prove. And I'm going to specify 4 n being an element of the set of all positive integers. Now what we did in terms of the domino analogy, we first proved that the first domino fell. So we proved that our claim was true for the first value. Then we picked a random domino, we called it k, and we assumed that it fell. So in this case, we picked a random positive integer and we assumed that it satisfied the claim. And finally, we proved that the domino next to that one actually fell. So here we proved that the integer next to that k, the k plus 1, satisfied the claim, meaning that when we plugged in k plus 1, that this side is indeed equal to this side, and we managed to prove that this side is indeed equal to this side using the inductive hypotheses. So what we managed to do is prove a rule, and that rule is if we pick any kth domino, it could be any domino, and it falls, then that means that the next one, the k plus 1 domino, will also fall. That is the rule that we just proved. But that rule is just an implication. Think about it. It's an if this, then this. Remember that this is our claim. It could also be rewritten as p events or proposition at n, and this is a proposition. It could be true or false depending on what n is. And our rule says, okay, if we assume that our claim, so our p, our proposition at n, is true at n is equal to k, so if this is true, then what? Then we showed that the claims or proposition at n is equal to k plus 1 will also be true. This is the rule that we proved. So how can we use this rule to prove that all of the dominoes will fall at the end of the day? Because really, we don't know that this one falls. So really, all of the dominoes are still standing up right now. And our rule only works if the kth domino falls. So in order to use this rule, we need to find a domino that falls. And luckily for us, we know a domino that actually falls, the first one, because we proved it in the basis step. And so if we know that this one falls, if we know that our claim is true at some kth domino, because again, the kth domino could be any domino, if this is true, then that means that the claim is true for the next domino, which happens to be the domino right next to it. So that means that this one also falls, which sets up a beautiful chain of reaction, because what if we said that this is our kth domino now? Remember that our rule says that if our claim is true for some kth domino, which we know it's true here because we know that this fell, then the claim is true for the next domino. So that means that the kth plus 1 domino, the next domino, also falls. Then if we say that this is our kth domino, then our rule says if that kth domino falls, which it does, then the next one, the kth plus 1 domino, will also fall. Now if this is our kth domino, our rule says if that kth domino falls, which we know it does, then the next one, the kth plus 1 domino, will also fall. And then if this is our kth domino and we know that it falls, then our rule says then the one right next to it will also fall. And so you'll see how it's going to continue on forever. So all of the dominoes will fall, all of the positive integers will satisfy the claim. So in the context of this problem, we prove that if the claim is true for some integer k, that implies that the claim is true for the integer right next to, right after that k. And to use this rule, we need to find an integer where the claim is true. We prove that the claim is true for 1 as the integer. So then we can use the rule and say, okay, if the claim is true for 1, that means that the claim is true for the next positive integer after that. And then that starts a chain of reaction, because then 2 is the integer where the claim is true. Then we can prove that the claim is true for the next positive integer after that, and so on and so on. So just like all of the dominoes fall, so will all of the positive integers satisfy the claim. And that is the beauty of induction. I'll see you in the next video.